Alright, hello everyone. This is Physics 2212 Lab 4, where we're going to be exploring DC and RC circuits. So the purpose of this lab is to utilize our understanding of node and loop rules, as we've been learning over the past few weeks, to make predictions on the behaviors of circuits that have resistors in series and parallel. And then we're going to use multimeters and which include ammeters and voltmeters, to verify these predictions. And then we're going to look further into RC circuits, in which RC stands for resistors and capacitors. In the following diagram, we're going to try to predict what the currents will look like at I1 and I2. So first of all, a quick note is if we have two batteries right here and each battery is 1.5 and they're in the same direction, well, we can just pretend that's just one battery that has 3 volts instead of two 1.5 batteries. So if we have a 3-volt battery, we can use Ohm's rule, which will be V equals IR. So we need to solve for the total resistance. Well, resistance, given we're in series, we can just add the value of the two resistors to get 147 ohms. Now, if we want to look at current, we got I1 and I2. Well, given I1 is immediately after I2, there's no breaks, there's no different nodes. I1 is going to equal I2. So we just got V equals IR, which will be 3 equals 147I. So I will equal 3 over 147, which is 0.02 amps. And like I said, that's I net, and I net equals I1, which equals I2, so we can say each I1 and I2 is 0.02 amps. So let's see if that's right. Sure enough, it is, using this FET simulator. By plugging in ammeters for each spot where we are solving for I1 and I2, we can see that our predictions were correct. Now, of course, if we switch upside down the ammeters, we're going to notice that 0.02 remains the same. It's not negative, it doesn't change the sign. And this is because, and as we'll discuss more later in this video, the ammeters don't have any resistance. They just simply measure the current going through them. So they don't really depend on the sign or the orientation of the ammeter. It simply just measures what the current will be given the flow going through it. So now if we replace an ammeter with a voltmeter, well, we can see in order to put in this voltmeter, we're going to have to break this circuit. And, well, if we break the circuit, we're essentially making infinite resistance. So there's no way for any current to go through. So that's why the current at the bottom reads 0. However, we are able to read voltage, as is the purpose of the tool. So we can see that our voltage is 3, which is reflective of having one 3-volt battery. Now we can measure the potential difference throughout the entire circuit at each different point. So notice how A to B going through that one battery, that's 3 volts, and positive 3 volts at that. Going across a wire or across an ammeter, that's 0, and that implies that the wire and ammeters have 0 resistance. However, when we go across actual resistors, we notice that we do have a drop in voltage. And notice how E to F has about double the drop of voltage as C to D does, and that's reflective of the fact that it has double the resistance, roughly, and V equals IR. And again, we can see this in the graph, how C to D only drops about halfway, that E to F does. Now, if we were to make a ammeter in parallel to the other ammeter, well, we can see we're kind of dodging this 100 ohm resistor. So by dodging that 100 ohm resistor, we're having more flow, more current dodge the resistors. Therefore, there is more current in the system given less resistance. And again, recall V equals IR. That's the biggest takeaway you can possibly have over this unit. So now we're going to explore capacitors. So we can notice that when we have an unshined light bulb, well, when we plug in this, when the capacitor is charging and the capacitor reaches a maximum charge, the light bulb goes out while it was shining as the capacitor was charging. And as the capacitor discharges, it shines the light bulb for a bit, but once it goes without charge, no current flows. And we can see that's because when it's at a max charge, it basically blocks the current. When it has no charge, there is no current flowing through the system. We can see that a higher ohm bulb takes further time or more time to charge or to discharge. We can explore this exact RC time constant by using the equations given in the lab doc, which make plenty of sense when you think about them. And by solving for data, we can get a very nice linear graph in which our slope represents the RC time constant. Well, we got to take the inverse of that. So our RC time constant is about 6 seconds exactly. I know I'm running out of time, but some final thoughts real quick. Ammeters, like wires, have no resistance. Voltmeters have infinite resistance as they separate the current. Um, and as I touched on earlier, the potential difference throughout a whole system, any point in this system, if you go through a whole loop, will equal net zero. Which again makes sense because when you have a resistor, it's going to take away some of the current or some of the voltage. Sorry, there's going to be a voltage drop. Capacitors block the current from flowing through them at full charge. When they discharge, no current flows through them. And we could solve for an RC time constant by simply measure the change in voltage and the time that it takes for that change of voltage to occur. Thank you for watching. Sorry I went over time a little bit. Have a good one.